this is a video about a EE278 final project. So this is basically an implementation of feature extraction algorithm on an FPGA. Uh, Me and my teammate Bharat have implemented this feature extraction using a C code. We have used a C++ prototype, and then we have implemented a C code with a hardware accelerator on an FPGA. So basically, let's talk about the feature extraction algorithm first. So this is the paper we have referred for the feature extraction algorithm. So as we can see, the feature extraction is basically extracting particular features from an image. So suppose we choose an image which is like an 8x8 or a 256x256. There are particular feature points which you want to extract from an image uh, for your purpose. So that we would be doing it through a feature extraction algorithm. So this is the feature extraction algorithm we are using. As we can see here, it says that for an image which we have chosen, we'll be calculating for each pixel a values of A, B and C, which would be for a particular patch of an image. So basically A would be an Ix square, so Ix would be a gradient in the X direction and Iy would be a gradient in the Y direction. So A would be Ix square and B would be Ix into Iy and C would be Iy square. So basically we would be doing for every pixel which we would be extracting from the image. So after we calculate the values of A, B, C, we would be using the equation Pij A minus T C minus T minus B square. So basically we will be extracting features based on this particular feature where it says that if Pij is greater than 0 and Aig is greater than threshold, then we retain the pixel values I and j. So basically that would be our feature points which we would be using from our image. And when we have implemented, we would be extracting a lot of feature points, and as we can see, we would be picking out the particular features based on the enforced minimum distance. So this is done to keep a minimum distance between the features. So as you see here, the minimum distance feature is used because we get a cluster of features once we implement the algorithm. So we would be picking up the particular features which we want based on the minimum distance. So we have, as I said, we have implemented a C code. So I'd go ahead and show you the C code which we have implemented as a prototype, and we'll show the values which we have features which we have extracted. So we have created a feature extraction file. So this is our file which we are using, and we'd like to show you the image. So this is the image which we are using for our feature extraction algorithm. So this image would be an input file to my C++ code. So let me show you the code here. So this is my C++ or C code, which will basically read the image and then create an array of the pixel values. So if you can see here, I calculate the width and height of the image, so and the size of the image which I would be using, and this would be creating a dynamic array of the pixel values of the image. So as you can see here, this would be the BMP file which I would be reading. So once I have read the image file, I would be creating a dynamic values of arrays of all the pixel values. So that would be an input to my code. So this is like the feature, the logic basically for the feature extraction. So we have used the corner detection algorithm where we'll be calculating for each pixel values, we'll be calculating the left, right and top and bottom for each of the patch. So suppose we calculate the x gradient, y gradient as well as these as x value and the y values, and we would be displaying those values out, and that would be our feature points. So as we can see here, this is the Pij or the Pij algorithm which we are using as per the document. So we'll be using the same equation to calculate the values, and then once we go here, I would be displaying the values. So it says the corner has been detected, and then I have an enforced minimum distance algorithm where I calculate the minimum distance and display the minimum values. So let's start the implementation here. So once I click once I start debugging, so as you can see, I have chosen an 8 cross 8 from the image pixel values. So basically this is for the this is in terms of the memory which we'll be using for the hardware accelerator to maintain uniformity. I have chosen an 8 cross 8 for the C++ code too. So basically this is my array of C plus which I have extracted the dynamic array from the image. So these are the pixel values, which is the 146, 146, 146, 49, 49, 49, 65 and 0. So this will be the row values of the pixels of that image. So using that and using my logic, I'll be calculating the dx and dy. Basically that would be the corners. So as you see, once the dx and dy value has been found out based on the threshold, so here in terms I had chosen a threshold of 50. So I'll be using the same threshold. So I've chosen a threshold of 50. So based on that, my logic gives me corners at a lot of places. It would be 1 6 2 0 2 1 2 3. So there would be a lot of corners which are getting detected, and based these are the final values are the my actual corners which will be displayed out based on the feature points. So basically this is where the enforced minimum distance is being used, where based on the minimum distance we extract the particular feature points. So let's start with the hardware implementation of this. Basically that would be the hardware accelerator implementation. So we have done a C code. To show you here, we'll have implemented the same code, but basically we would be doing the matrix multiplication using the hardware accelerator. So this is like the ix values, which the x gradient values which you have extracted, and iy values which will be the y gradient values which you have extracted. So basically those two multiplication we are doing it using an hardware accelerator. So let's start the process. Let's open the quarters. So basically I would start from the first. So create a new project wizard. So here I'll create a new folder for my implementation. Say I will name it as a feature extraction. So I select this folder and I name the project, and then I click on next. We don't have any files to add now, so I'd go ahead and with the empty files. So next would be I would select the family as Cyclone 2, and then the package as FPGA, pin count as 484, speed grade as 7, and then we select the available devices. As said, it would be EP2C20F4484C7. So I would go next, and for the simulation we would be using model sim Altera, and my format would be basically Verilog HDL. So hardware accelerator which I have is implemented in Verilog, so we'll be using a Verilog HDL. So I click on next and then I finish. So let's go ahead and launch QSys, where we'll be basically connecting our hardware accelerator code here. In QSys we have a lot of component libraries, so we would be using the existing component libraries to create the interface. So as we see here, we go ahead and add the NIOS to processor, and then we select the NIOS to core. We would be later changing the reset vector as well as the exception vector. So let's click finish for now, and then next we would be adding an on-chip memory. So for using purposes we can use 8K memory. So that is how much we would need, since there's a lot of array which has to be run, and there's a lot of computations which has to be done. So I select an 8K memory, and then we need a JTAG UART. For the this is basically an interface protocol which would be adding here, and then of course a performance counter which will give me the number of cycles basically which my code takes. So I click on finish here. So I have added all the component libraries which I would be needing. So now I would go ahead and create a new component. So let's name it as FE, that would be a feature extraction. Change the description, and then I would like to add my hardware accelerator code here. So I would add my hardware accelerator code here, and then let's click on analyze synthesis file. So basically this would analyze all the files, all the code which is written there. Okay, as we can see there are 0 errors and 0 warnings. So let's go to these are all the files which I have. So this would be s0, read data, write data, and address. And let's come to interface, where it says that we would be associating a clock as a reset. Okay, so as we can see there are no errors and warnings, so we can just go ahead and finish it. So I click on save. So I have added the new component here, so I'll go ahead and add it to the interface. So as we can see it's added here. So now let's connect all the interface modules. So basically let's start with the clock. So clock would be given to all the modules. So click on clock. Let's make all the connections. And then it would be a clock reset. So we would be connecting a reset to all the signals. And then from the data master we would be giving it to an on-chip memory, so S1. And then from an instruction master, so from an instruction master, as you can see, it has to go to the Avalon JTAG slave, as well as the control slave, as well as the S0. And then this would be the outside clock which would be giving, so clock in reset. And then this would be the interrupt which would be selecting. So now we would go to system and assign the base address for all the modules. So as we can see, all the base address has been assigned. So let's go to NEOS2, and then here we would, as we can see, there are 2 errors, and there's, for the reset vector memory, go ahead and select the on-chip memory, and exception vector memory, go ahead and select the on-chip memory. So when I click on finish, as we can see there are 0 errors and 0 warnings. So let's go to generation, and then in the generation, so let's click on generate. It will ask us to save the file, so we can go ahead and save this file. So this is going to take a while to generate. So once the generation is done, we would go ahead and add the files in the Cortex 2. Okay, so there are 0 errors and 0 warnings. So let's go to Cortex, and let's go to files now. So let's click on add and remove files. So we will be basically adding a new file here from the synthesis. It would be a QIP file. So this is the one which we created during the generate. Okay, click on OK. So we would set it as a top level entity, and then let's go to the pin planner. sorry, the assignment editor. He would here, as we said, as we have given an outside clock, so we would be creating a clock input here for clock, and then we would be selecting location, and the value would be a pin underscore L1. We would be creating one more instance for the clock. It says clock, and this would be basically the IO standard, and then we would be selecting the 3.3V LVTTL value. So let's click on, so let's save this and let's click on the start compilation. So this would be compiling all the files under this particular QIP file. So as we can see, it is all it as the fully compilation was successful. So let's go ahead and click on the programmer. So basically here we would go ahead and add a file, which would be from the output files, the .sof file. Sorry, that would be a different file. Okay, so that would be an SOF file here. So let's click on start. So as we can see, the connection was successful, and then let's go ahead and save it. So we would be saving this under the output files. Okay, so let's now go back to Cortex. So we would be launching the NIOS to Eclipse tools, and this tools here will try to run a small program to see if it is working fine, and then we would go ahead and add our code with the C code and the hardware accelerator here. Okay, so these are the previous instances, so you'd go ahead and delete them. You'd create new instances and then run it here. So let's go ahead and create a new NIOS2 template, application template. So we'll have to pick the SOPC file from the feature extraction folder which we had created. So let's name this file. Let's give a project name. Then let's select the hello world small program. So this would let us run the let us verify the connection. So once this file loads, okay, so this, as we can see here, the hello world small file .c is generated. So let's go ahead and build the project. So once we build this project, next we would go ahead and run this using the NIOS to hardware, and then we would go ahead and add our file to the hello world file and then run it and then compare the outputs. So we can, as we can see, so this, as I was saying, this would be our C code as we have modified it. So we have added for the matrix multiplication, we have added the hardware accelerator. So we can see that the A, B, C values are getting calculated using the hardware accelerator. So basically the multiplication operation is done using the hardware accelerator. As that was as said in the project status report and as well as the project demo. So let's see if it is. Okay, so the build hasn't finished, so we can go ahead and run the program using the NIOS to hardware. So once we run, we should be successfully able to get a message. So this is the message we are expecting, hello from NIOS 2. So this is the file. So we will go ahead and add our file to this and then run it using the hardware accelerator. So let me explain the code here a bit. So this would be basically the test cases which we are calculating. So it would be all IO read and IO write for ABC values. So basically the inputs would be an IX and IX. So these are the IX and IY. So A would be IX into IX, and that would be done using the hardware accelerator for matrix multiplication. So let's go ahead and add the file here. So let's save it. So when I go ahead and run the code, I should be able to successfully extract the points. And display the outputs here. So based on that, we can verify with the C++ prototype as if it is working fine. So we are successfully able to build it. So as we can see here, these are the values which are loaded here. So let's go ahead and compare with the prototype which we have for the C++. So this is the prototype and the arrays which we have used. Of course, both the codes would have the same threshold and both the values would be matching. So as we can see here, the FL values would be basically the minimum distance values which we had calculated. So as you can see, they match here, and then we have these are the actual corner points which are feature points which are extracted from the code. So as we can see, the first would be the 5-1, the 1-6, 5-6, 5-0, 2-3, and basically if you can see here, these will be the ABC values. So these are all the values which are generated, and these are the feature points which we have extracted from the code. So as you can see that both the outputs and the prototype matches here. And we were successfully able to implement the feature extraction algorithm. So as we can see here, so as per this, we have implemented all the algorithms here, including the A, B, C values, and then we have calculated a pixel patch for PIJ for each of the values, A, B, C values. So basically this would be done for any kind of an image. So we have made sure we have created a dynamic code where we would feed in the image values and it would generate a dynamic array of values using our C++ code. So basically we are directly feeding in the image. So any kind of grayscale image would be chosen. So in this case, as we have mentioned before, we have chosen a grayscale image too, and that was fed to a C++ prototype that would generate an array of all the files, and that files would be used here. So and then we have calculated all the values, and basically using the minimum enforced distance, we have printed out the values for the output. So if you can see, that is the project which we have implemented, and this is like the feature extraction algorithm on FPGA. Thank you for watching. Thank you.